All right, we're diving deep into operating systems today.
Really deep.
Yeah, you guys sent in excerpts from textbooks, academic papers.
The whole 9 yards.
Exactly. You really want to understand how operating systems always really work.
I think what's cool is that you're not just looking for the surface level stuff.
Right.
You want to understand the core principles.
The why.
Yeah, the why behind the what.
Like taking apart a clock
Exact.
to see how all the gears mesh together.
Yeah, how each little tiny piece contributes to this whole symphony of timekeeping.
So we all know that operating systems do a lot.
Right.
They manage files,
Uh-huh.
they run programs, they make the computer usable, but it's
Yeah.
easy to just take it for granted.
Absolutely.
Like, what's actually happening when I open 10 different apps and my computer doesn't explode?
Yeah, that's a great question. That's where understanding processes comes in.
Okay.
So it's not just that the apps are open.
Right.
The OS treats each one as like its own little world. A process with a life cycle.
Well,
Different states.
yeah.
Running, waiting, sleeping.
Oh, okay.
Imagine a chef juggling all these different dishes at once.
Okay.
That's the OS managing CPU time for each of these processes.
So even though to me it feels like everything's happening at the same time, the OS is really just giving each of those processes a tiny slice of CPU time and switching between them so fast I don't notice.
Exactly.
But how does it decide who gets to go next? Does it just pick randomly?
That is an awesome question, and the answer is absolutely not. This is where scheduling algorithms come in.
Okay.
And this is where it gets really cool. There's all these different approaches,
Right.
each one with its own trade-offs. Some prioritize speed, some prioritize fairness, some are better for interactive tasks versus background processes.
So like different tools for different jobs.
Absolutely.
Okay.
It's kind of like, imagine you were trying to manage 100 hungry customers in a restaurant.
Oh, gosh.
The OS has to figure out how to keep everyone fed with CPU time
Right.
without starving anybody.
Without crashing the kitchen.
Exactly.
But, okay, backing up a little bit, how do these processes even come into being in the first place?
Good question.
Is it just when I, like, double-click on the app icon?
It's a little more involved than that.
Okay.
There's a really key concept here,
Okay.
highlighted in a lot of the sources you sent. It's this thing called the fork system call.
Okay, fork.
So imagine like a family tree.
Okay.
Parent process can use fork to create a child process.
Huh.
And that's an almost identical copy.
Hmm.
And then that child can fork its own children,
Okay.
and so on and so forth.
So it's like this constantly branching tree of processes all working together. But surely they can't all just do their own thing in isolation, right?
You're absolutely right.
They have to talk to each other.
They've got to cooperate, share information.
Right.
The readings talk about this thing called interprocess communication, IPC.
Okay.
It's this whole world of mechanisms that let processes exchange data and coordinate their actions.
I'm picturing like memos flying back and forth and people huddled in conference rooms trying to
It's a good analogy.
get on the same page. But on a computer, what does this communication actually look like?
That's a great question. So your sources delve into some fascinating examples.
Okay.
One is called shared memory. It's like having a common whiteboard where processes can read and write data.
Okay.
Another one is message passing.
Okay.
That's more like sending emails or text messages.
Uh-huh.
Processes can send these structured messages back and forth to each other.
Got it.
One classic problem they use to illustrate this is the producer-consumer problem.
Ooh, okay, what is that?
So imagine one process is churning out data.
Okay.
Maybe it's reading from a sensor or doing calculations.
Okay.
And then another process needs to take that data and do something with it.
Process it.
Exactly.
I've got it.
They need a way to hand off the data without stepping on each other's toes.
Right.
That's where a shared buffer comes in.
Okay.
And that buffer is managed very carefully through IPC.
So process 1 drops the data in the buffer.
Mhm.
Process 2 grabs it when it's ready.
Yep.
And the OS makes sure they don't both try to access it at the same time.
Exactly. It's like a relay race, passing the baton
Yeah.
without dropping it.
Right. Exactly. But where does all this data actually live?
Yeah.
You've got these processes running, talking to each other.
Yep.
But they need somewhere to store their stuff.
You are thinking about memory management.
Okay.
This is one of the coolest and most ingenious aspects of how operating systems work.
Okay, so this is important.
This is a big deal.
Okay.
Your readings spent a good chunk of time on this.
Okay.
And for good reason. because it's all about illusions and clever tricks to make the most of limited resources.
Illusions. Okay, I'm already intrigued.
Yeah.
Isn't it just about having enough RAM? Like my computer has 16 gigabytes of RAM. Shouldn't that be enough for anything?
Well, not so fast. It's not that simple.
Right.
The OS doesn't just hand over all 16 gigabytes to your programs willy-nilly.
Right.
It has to manage things very carefully.
Okay.
And that's where the difference between physical memory and logical memory comes in.
Wait, so there's more than one kind of memory.
That's right.
I'm starting to see why you called it illusions before.
Okay, so think of physical memory as the actual RAM chips in your computer.
Okay.
That's the physical space that you have to work with.
Right.
Logical memory is what the OS presents to your programs. And through these techniques, like virtual memory,
Okay.
it can actually be much larger than physical memory.
My mind is officially blown. So you're saying my computer can act like it has more memory than it actually does?
Exactly.
How is that even possible?
The key is this concept called swapping.
Swapping.
Imagine you have a giant bookshelf, but you only have a small table to work on.
Okay.
You can't put all the books on the table at once.
Right.
So you keep the ones you're actively using on the table.
Right.
And then you swap the others back to the bookshelf when you're done with them.
So the OS is constantly like moving data back and forth between RAM and the hard drive depending on what's needed at the moment.
You got it.
That's a lot of juggling.
It is.
It's very impressive. And it gets even more complex when you consider that modern OS don't swap entire programs.
Right.
Typically.
Right.
They break the memory down into smaller chunks called pages
Yep.
and swap individual pages as needed.
Exactly.
So it's like having this library of books, but instead of moving entire bookshelves, you're just taking out the specific pages you need and putting them on your desk.
Perfect analogy.
But how does the OS keep track of all this?
Yeah.
It must be a logistical nightmare.
That is where page tables come in.
Page tables. Okay.
Think of it like the library card catalog.
Okay.
You have this virtual address that corresponds to a page,
Uh-huh.
and the OS uses the page table to translate that virtual address into an actual physical location,
Right.
either in RAM or on the hard drive.
Gotcha.
And then to make things even faster, there's this thing called a TLB.
TLB. Okay.
It's like a cache
Okay.
that stores the most recently used translation.
Like a little cheat sheet
Exactly.
for the most popular books, so you don't have to keep looking them up in the card catalog every time.
Exactly.
But this is all happening behind the scenes.
Yes.
Right? I, as the user, I don't even have to think about this when I'm using my computer.
That's the beauty of it. The OS is managing all of this complexity
Yeah.
so seamlessly that you can just focus on what you want to do.
Right.
Whether it's writing a document, browsing the web, playing a game.
Right.
But under the hood,
Underneath it all.
there is this intricate dance of processes, memory, data,
Yeah.
all orchestrated by the operating system.
It's a beautiful dance.
It is a beautiful dance.
Okay, so we've covered processes running, chatting with each other, cleverly using memory. But where does their data actually live long term?
Yeah, okay, you're talking about file systems now?
That's right, file systems. And I bet there's a lot more to it than just dragging and dropping files into folders.
Oh, yeah, absolutely. File systems are how the OS organizes and stores all of your data.
Okay.
Everything from documents, photos,
To the programs themselves?
to the programs themselves. What you see as folders and files is just the tip of the iceberg.
Right.
Underneath, it's all about blocks, sectors, and these really clever algorithms for managing disk space.
So it's not just a digital filing cabinet?
Not quite.
Okay.
Think of it more like a vast library with different sections, shelves, and books.
Okay, I like that analogy.
Yeah. Your sources actually highlight the evolution of file systems.
Oh, cool.
From these simple single-level directories to the more complex tree-structured systems that we use today. Do you remember figure 11.1?
Yes.
That visual comparison?
Yeah, that was really helpful.
Yeah, it really helps to grasp the difference.
It shows how a two-level directory system lets you group users and files, but the tree structure really takes things to a whole new level. But it's not just about the directory structure, right? How does the OS actually decide where to put the data on the physical disk?
That's where file allocation methods come in. It's like deciding how to arrange the books on the shelves of our library.
Right, right.
So you have contiguous allocation, where a file takes up a block of space all in one piece, like having all the volumes of an encyclopedia right next to each other.
Right, okay.
Then you have linked allocation,
Okay.
where a file is kind of scattered across a disk,
Uh-huh.
with each block pointing to the next, kind of like a treasure hunt.
Okay.
And then finally, you have indexed allocation,
Okay.
which is like having a table of contents for the file, telling you exactly where to find each piece.
So I'm already starting to see like the pros and cons of each approach.
Yeah.
Like contiguous seems easy to manage,
Uh-huh.
but what happens if you have a big file and there's not enough consecutive space?
Exactly.
And then linked seems flexible, but wouldn't it be slow to have to jump all over the disk to find the pieces?
You're getting it. Each method has its own trade-offs.
Right.
And OS designers have to carefully consider things like speed, efficiency, and the likelihood of something called fragmentation.
Right, fragmentation.
Your readings do a really good job of illustrating these trade-offs with visuals and examples.
Yeah, those are helpful. But there's another crucial aspect of file systems we haven't talked about yet.
And that is security.
Security.
Of course.
Because it's not enough to just organize the data. We need to make sure that it's protected.
Right.
Both from unauthorized access
Yes.
and accidental damage.
You got it. And I bet this is where things get really interesting.
Oh, yeah.
Especially in today's world, where security breaches are a constant threat.
Absolutely. One of the sources put it very bluntly. They said, an unprotected resource is a recipe for disaster.
Oh, that's a good one.
So the OS is like the security guard for your system.
It is.
Responsible for making sure that only authorized individuals get access to sensitive information.
Exactly.
Yeah.
And just like a good security guard, the OS has different levels of access control.
Right, right. Like I remember reading about user permissions, group permissions, and something called a protection mask. Can you kind of unpack that a little bit for me?
Sure. So think of it like having different keys for different areas of a building.
Okay.
So user permissions determine what a specific user can do with a file.
Okay.
While group permissions apply to a group of users.
Gotcha.
And then the protection mask is like this set of bits that specify exactly which actions are allowed.
Okay.
Like reading, writing, executing, and so on. It's all about fine-grained control, making sure each user and each process only has the privileges they absolutely need.
So it's like this complex web of permissions carefully woven by the OS.
Exactly.
To keep everything secure.
Exactly.
But it's not just about those external threats, right? What about like internal mistakes? Or even malicious programs that try to exploit vulnerabilities?
You are hitting on a really, really crucial point.
Okay.
One of your sources describes buffer overflow attacks.
Okay.
This is where malicious code can overwrite parts of memory.
Right.
And potentially gain control of the system.
That's a little scary.
It is.
Yeah.
And then there's a classic example mentioned in the readings as well, the Morris Internet worm.
Right. Yeah.
That exploited buffer overflows to spread across networks and wreak havoc.
And that highlights just how important it is for OSISs to have these robust security mechanisms in place.
Absolutely.
Especially as systems become more complex and interconnected. Which brings us to a whole other dimension of complexity.
Which is?
Distributed systems.
Distributed systems.
Dun, dun, dun.
Yes. This is where it gets really interesting.
Okay, this is where it gets really interesting. We touched on this concept earlier, but I'm ready to go deeper.
All right, let's go.
What makes them so different from those single computer systems that we've been talking about so far?
Okay, so think of it like this. Everything we've discussed so far.
Processes, memory,
files, security, all of it.
Okay.
Gets amplified in a distributed system.
Okay.
So imagine coordinating not just the processes on one machine, but across a whole network of computers.
Whoa.
Each with its own resources, each with its own quirks, each with its own potential points of failure.
Okay, so the complexity just explodes.
It explodes.
Like going from managing a single household to running an entire city.
Exactly.
It's a lot to keep track of.
And just like a city needs this robust infrastructure to function properly, distributed systems need all of these sophisticated mechanisms for communication, coordination, and security, especially security.
So we're not just talking about files and folders anymore. We're talking about coordinating data, resources, and actions across multiple machines. Potentially spread across the globe.
Across the globe.
What are some of the key challenges that come with that level of complexity?
So one of the biggest challenges is maintaining consistency.
Okay, consistency.
Think about like a distributed database.
Okay.
You might have multiple copies of the data stored on different machines. But you need to make sure that all of those copies stay in sync.
Yeah, so they're all telling the same story.
Exactly.
Okay. But how do you even begin to address that kind of problem?
That's a great question, and this is where things get really, really interesting. So your readings mentioned something called distributed consensus.
Distributed consensus.
Okay, these are algorithms that help to ensure that all the machines in a distributed system agree on a single truth.
Okay.
Even in the face of all this adversity.
Even when things go wrong.
Even when things go wrong. So imagine a global network of banks.
Okay.
They need to all agree on account balances,
right.
transactions, all of that stuff, while dealing with network hiccups.
Right.
Potential attacks.
Failures.
Exactly.
Yeah.
So it's not just about keeping files in sync. It's about making sure every computer agrees on the truth.
Right. Even when things go wrong.
Even when things go wrong.
But how do you get a bunch of computers to agree on anything when they can't even see each other?
That's the genius of these algorithms. Your sources highlight two in particular.
Okay.
Paxos and Raft.
Okay, Paxos, Raft.
And they rely on all this clever message passing, voting mechanisms, and timeouts to reach this shared understanding. Imagine like a group of explorers charting a course through this dense jungle.
Okay.
They have to constantly communicate their positions, adjust their plans, make sure no one gets lost. That's kind of what these algorithms are doing.
I can see how I'm starting to see the complexity. But it still feels a little bit like magic to me. Like, how can you be sure that every machine eventually arrives at the same conclusion, even if messages get lost or delayed?
It's kind of like a rumor spreading through a community. Eventually, everyone hears it, even if there's some initial confusion or misinformation.
Okay.
These algorithms are designed to tolerate a certain degree of failure.
Right, so it's not about preventing errors or delays altogether.
Right.
It's about building a system that can handle them and still reach a consensus.
Exactly. It's about being resilient.
But why go through all this trouble?
Right.
What are the real-world benefits of having this distributed consensus?
The implications are huge. Think about online shopping.
Okay.
You click purchase.
Right.
Instantly, databases across the globe are updating inventory, processing payments, scheduling deliveries.
Right.
Without distributed consensus, this whole seamless experience
that we all take for granted
would be impossible.
Yeah, it's like a perfectly choreographed dance with every computer playing its part in perfect harmony.
And that harmony is what makes distributed systems so powerful. They let us scale our applications beyond the limits of a single machine.
Right.
Handle these massive amounts of data.
Yeah.
Build services that are resilient to failures.
So they're really the foundation of a lot of the technology that we rely on every day.
Absolutely.
Okay, well, this has been incredible so far.
Yeah.
We've covered so much. Processes, memory, files, security, now these distributed systems.
We've been on a journey.
But we're not done yet.
No.
There's still so much more to explore in the world of distributed systems.
I'm ready when you are.
Let's do it.
So distributed systems, it's like this complex web connecting multiple computers to work together as one. But getting them to play nice, well, your readings make it clear it's no easy feat.
My head's already spinning just thinking about it. We went from managing processes on one computer to coordinating actions across multiple machines. What kind of problems does that create?
One major hurdle is making sure everyone has the same information. Imagine a group project where everyone's working on separate documents, no shared workspace.
Oh, that's a recipe for disaster.
Right, that's the challenge of consistency in a distributed system.
Version conflicts, outdated info, chaos. How do you even begin to address that in a distributed environment?
That's where distributed file systems, or DFS, come in. Imagine accessing any file from any computer as if it were all in one giant seamless folder.
Like a universal library card. Access any book, any branch, no matter where you are.
Exactly. But making that experience seamless, well, that takes some serious magic behind the scenes. Think about Google Docs, multiple people editing at once.
Right.
Real-time synchronization, conflict resolution, that's no easy feat.
I've definitely had those moments where two people are typing in the same paragraph and things go a little haywire. Never realized how much goes into making it work smoothly.
It's a testament to operating systems and those who design these systems. Network latency, potential failures, even malicious actors.
Yeah.
They have to think of it all.
So we've got these distributed file systems, making it feel like our data's in one place. What about the programs themselves? How do they coordinate in this distributed world?
Things get even more interesting there. Remember, IPC, interprocess communication.
Right, the memos and whiteboards.
Well, now it's not just processes on the same machine. It's across the network.
So messages flying across networks instead. Doesn't that open a whole new can of worms? Delays? Dropped messages? How can you be sure things work reliably?
That's what researchers and engineers have been tackling for decades, a constantly evolving field. One thing your sources dive into is message queues.
Message queues, like a line at the post office.
Similar concept. It's a buffer between processes. They send messages without needing to be directly connected, like sending a letter.
You don't have to wait for the person to be home to drop it in their mailbox.
Exactly. The Postal Service ensures delivery eventually.
So a message queue is like a reliable postal service for distributed systems?
That's a great way to put it. Adds robustness and flexibility, especially with unpredictable networks.
Okay, we've got messages flying, data syncing, virtual machines doing their thing. But how do you protect all of this? Security has to be an even bigger headache now, right?
Absolutely. Security is paramount in distributed systems. One weak link, and the whole thing's compromised. Your readings highlight this, starting with secure communication.
So making sure the messages themselves are protected, encrypted, like putting them in a locked box before they're sent.
Exactly. Encryption turns those messages into gibberish without the right key. But it's not just about the message in transit. You need to know the sender and receiver are legit.
Right. If you can't trust the other machines, it's like letting strangers into your house without checking their ID.
That's where authentication comes in, verifying the identity of each node.
Digital bouncer at the door, checking credentials. Got it. So secure communication, authentication, what else?
Access control is still crucial. Just because a node is in the system doesn't mean it gets access to everything.
Right, like giving the mailroom clerk access to the company's financial records.
Right. Exactly. Each node needs permissions for its job, just like a well-run organization.
But enforcing those rules in a distributed environment where everything's spread out, that's got to be a whole other challenge.
It is. Robust mechanisms and careful planning are key. Your sources talk about distributed authorization, managing permissions across the entire system, not just on individual machines.
So a central security policy that applies everywhere.
Precisely. And that's just the tip of the iceberg when it comes to distributed system security. There's so much happening in this field as threats evolve.
I'm starting to feel a little overwhelmed, honestly. We went from the basics of processes and memory to this world of distributed systems and security protocols and algorithms I can barely grasp.
Understandable. It's inherently complex. But you don't need to be a computer scientist to appreciate it all. Think about what we rely on every day. Cloud storage, online gaming, streaming. It's all powered by distributed systems.
True. It's easy to take for granted, but understanding even the basic concepts makes you appreciate the magic behind it.
And speaking of magic, remember those distributed consensus algorithms. They make the impossible possible. Ready to dive into that rabbit hole?
Lead the way. Okay, so distributed consensus. Let's break this down. Sounds like something out of a sci-fi movie.
Right. Computers across the world making a unanimous decision.
Exactly.
It's not as far-fetched as it sounds.
Okay.
These algorithms are essential for reliable distributed systems, making sure everyone's on the same page, even when chaos hits. Like, imagine a global network of banks.
Okay, yeah.
They need to agree on things like account balances, transactions, all while dealing with network issues and potential attacks.
So it's more than just keeping files in sync. It's about making sure every computer agrees on what's true.
Exactly.
Even when things go wrong.
Even when things go wrong.
But how do you get computers to agree on anything when they can't even see each other?
That's the brilliance of these consensus algorithms. Your sources focus on two, Paxos and Raft.
Okay.
They use clever message passing, voting, timeouts, all to reach that shared understanding. Imagine a group of explorers charting a course through a jungle.
Okay.
They've got to constantly communicate, adjust their plans, make sure nobody gets lost.
So a lot of back and forth.
A lot of back and forth.
A lot of potential for things to go wrong.
Exactly.
But it still feels like magic. How can you guarantee everyone reaches the same conclusion even with messages getting lost or delayed?
It's kind of like a rumor spreading. Eventually, everyone hears it, even if there's initial confusion or misinformation.
Okay.
These algorithms are built to handle that, to tolerate some failure, ensuring that the truth eventually prevails.
So it's less about preventing errors and more about being able to recover from them.
Exactly. Resilience is key.
Okay, that makes sense. But why go through all this trouble? What's the payoff of distributed consensus in the real world?
The impact is huge. Think about online shopping. You hit purchase, and instantly, Databases all over the globe are updating inventory, taking payments, scheduling shipments.
Right, and it all seems so easy.
Right. But without distributed consensus, that seamless experience, forget about it.
Yeah, it really highlights how crucial these systems are to the things we take for granted every day.
Absolutely. And that's what makes distributed systems so powerful. Scaling beyond a single machine, handling massive data, building services that can handle failures.
It's been an amazing journey, this deep dive. Processes, memory, files, security, this whole world of distributed systems.
It's been quite a ride.
It has. And I think the biggest takeaway is that operating systems, they're the unsung heroes of our digital world.
They really are.
They're behind everything we do with computers.
The invisible hand making it all happen.
And to our listener, if this sparked your curiosity, remember, this is just the beginning. There's a whole universe out there to explore when it comes to operating systems.
Keep digging, keep questioning, keep learning.
And who knows, maybe you'll be the one designing the next generation of these amazing systems that power our world.
The future is waiting to be built.